So the combined gas law is one that shows a relationship between pressure, volume, and temperature for gases. Okay, and the statement of the combined gas law usually looks like this: PV over T equals PV over T. And we might consider these to be the initial conditions, and I'll call those 1. And the final conditions, and I'll call that 2. Okay? So pressure times volume divided by temperature. Pressure and volume need to be in the same units when you do these calculations. And the units of temperature has always to be in Kelvin. Okay, for this relationship to work, you have to use absolute temperature. Okay? All right. So here's an example problem. A 3.5 liter cylinder, 25 degrees C, 2.5 atmospheres. And we heat it up until the pressure reaches 15 atmospheres. What is then the final temperature? Okay, temperature in Celsius. Well, the first thing we need to do is convert 25 degrees into Kelvin, because to convert to Kelvin, we're going to add 273.15. Okay, and so we get 298.15 kelvins. Just to back up here a little bit, if you think about this temperature scale here in the PV over T form, if T went to 0, that would cause all sorts of problems mathematically. Okay, so temperature must never reach 0. And in the Celsius scale, temperature certainly could go to 0, and that's why we use the Kelvin scale. Again, Kelvin based on the concept of absolute 0. And so 0 Kelvin, absolute 0. So you don't have to worry about your denominator going to 0 and causing all sorts of problems. Okay, now back to our original problem. We've converted to kelvins. That gets us out of some trouble. Let's just see what we've got. I'm going to make a little table here. V1, T1, P1, V1, and T1. And then I also want to write down my final conditions. My initial volume is 3.5 liters. My initial temperature, 298.15. And my initial pressure was 2.5 atmospheres. Okay. The temperature goes up to 15 atmospheres, or the pressure rather goes up to 15 atmospheres. Because this is a steel cylinder, the volume is constant, 3.5 liters. Okay, and temperature is the one thing that we don't know, the final temperature. So that's what we want to solve for. So our P1 V1 over T1 is going to be 2.5 atmospheres, 3.5 liters, 298.15 kelvins. And that's going to equal my final conditions, which are 15 atmospheres. My volume is still 3.5 liters, and T2 is what I do not know. If you have an equation and two things are the same, you can actually divide them out. So I'm going to start this process by dividing out 3.5 liters. Divide both sides by 3.5 liters. That simplifies my equation quite a bit. I'm going to solve for T2, so I'm going to bring T2 around to this side. Multiply both sides by T2. And that causes my T2s to divide out. I'm going to rewrite this to make a little more room. T2, 2.5 atmospheres. Equals 15 atmospheres. So now what I need to do is get my T2 by itself. I'm going to multiply both sides by 298.15. And that causes these to divide out. And then I'm going to divide both sides by 2.5 atmospheres. Okay, so now I've got T2 by itself. T2, 15 atmospheres. All divided by 2.5 atmospheres. And when I solve for T2, I get 1,788 Kelvin. Okay. And so to convert that to Celsius, I'm going to subtract 273. Okay. And we can disregard our 0.15 there, and we get 1,515 degrees C. All right. Let's take a look at a different problem then. It's showing that there's more than one kind of problem you can solve here. In the last problem, the volume was constant. I'm just going to start by setting up my table. All right, so here we have a helium balloon with a volume of 6 liters, okay, at 22 degrees C and 1 atmosphere. My final temperature I see is minus 18 degrees C. My final volume is what I'm trying to find. That's my question. And my final pressure, 0.55 atmospheres. So I need to add 273 to each of these in order to convert to Kelvin. So I've got 295 kelvins for T1. And I've got 255 Kelvin for T2. Okay. So my P1 V1 over T1, let's just write this, PV over T, is going to be 1 atmosphere, 6 liters, over 295. And that's going to equal 0.55 atmospheres. V2 I do not know, and 255 Kelvin. All right, so I need to solve for V2. I will multiply both sides by 255. And then if I divide both sides by 0.55 atmospheres, okay, that gives me the setup to solve for V2. And V2 is, I'll go ahead and write this out, 255 Kelvin, 1 atmosphere, 6 liters, 295 Kelvin, 0.55 atmospheres. This is my P2. Let's look at the way the units work. My kelvins divide out, my atmospheres divide out. My answer is going to be in liters. It turns out to be 9.5 liters. All right, so that's our helium balloon at high altitude.